today's webinar is going to be multi-cavity meshing workflow inside Moldex3D. So it's more of a tips and tricks presentation for the folks who are already using Moldex3D. And this is not only going to help you on the high cavitation. Yes, the focus is going to be on the high cavitation, but there is something, some takeaway, even if you don't have, high cavitation mold, just to get high level of accuracy with your simulation and mesh it much more faster. And I would like to introduce myself as well. I'm Harshal. Located in Chicago area, helping the team on the sales and implementation side of the business, and been in the simulation world since 9 years now, working with molding companies who are frustrated by production problems like shrinkage, warpage, air traps, and they're trying to figure out where is it coming from. Is it the part design, or is it the tooling or processing? And some of them are concerned by trial and errors that goes during processing and mold revisions. So trying to help them through Moldex3D simulations. So with that, let's get into today's topic. And it's a very short presentation, but I'll try to make it as much as useful for you folks in your work environment. All right, so today what we're going to do is we're going to look at the workflow for multi-cavity meshing, right? There are two major types. One is full model analysis, and another one is symmetry. What does full model analysis mean? Basically, what it means is, let's say you have a mold, you bring it in and you run the simulation on the complete mold, considering all the cavities, the entire runner system, everything, right? That's called full model analysis. And what is symmetry? Symmetry basically is running a simulation on a part of the mold, but getting all the information you would get, from running the full analysis. The benefit is you save so much time, energy, and resources, and get to the answer as fast as possible, right? So that's the benefit of symmetry. So we're going to talk about what is this and why do we do it, and when do we use it, right? We can also show you some buttons on what to click inside Moldex3D to run this symmetry setting. And then we're going to talk about different approaches, when it comes to like a multi-cavity tools and meshing multiple cavities and the runner system. One of them is the line-defined runner approach. So we'll talk about what it is, why line-defined runner is important, when to use it, and also we'll talk about the process on how to go about it inside Moldex3D. And another one would be solid geometry runner approach. Right, so we're going to talk about what it is, why we use this, in what situation we can use it, when we cannot use it, and so we're going to walk you through that process of what this solid runner meshing is. And towards the end of this presentation, what we're going to do is we're going to talk about cost-effective progressive analysis. What it means basically is how can we efficiently run simulation? What are different ways where we can shorten the simulation runtime, right? And majority of them, we're going to cover it today, which is through meshing, right? So we're going to talk about various different approaches, coarse grain versus fine grain analysis, single cavity optimization, considering the actual cavity, full runner system optimization. Like when you are at the stage where you are trying to optimize your runner design, like what do we need to do in that situation, right? So we're going to share some tips and tricks in regards to that. And then we're going to talk about combining both of them, right? Optimized cavity and optimized runner together for a complete, cost-effective progressive analysis, right? And it's going to be in progressive steps, right? First, we're going to run it on the part, and then we're going to go towards the runner, combine both of them to get our final analysis, right? So, but the overall idea is to save you time, energy, and resources when running these kind of simulations. All right, so we talked about the two major types. One is the full model analysis, and another one is symmetry. Full model, as I said, you bring in the complete mold. Let's say if you have a 32 cavity mold, you bring that in and you run a simulation on the entire 32 cavity mold, right? So that's called full model analysis. Then what is symmetry, right? Symmetry is basically running part of that 32 cavity mold, right? So we're going to talk about what is symmetry, what are the two approaches of when you are running these kind of symmetry analysis. What are the pros and also what are the cons of running these kind of analysis, right? So symmetry is basically a function inside Moldex3D to represent the entire model with similar number of cavities, right? And what we have is there is a half symmetry option and quarter of the symmetry option, right? And the level of the symmetry modeling will depend on the runner layout. So what it tells is basically, let's say you have in this particular image on the top right corner, you have this particular mold, right? We are looking at the top section of the mold from top to bottom, and we see that this is our rectangular mold, right? And let's say we have 32 cavities distributed in this, right? So what this half function does is basically we are running simulation just on the half of the mold, right? And what this quarter meaning we are just running the simulation in the quarter of the mold, right? So that's what it means. A full model meaning you are running the complete mold, half meaning you are just running simulation on the half of the mold, and quarter meaning you are running simulation on the quarter of the mold. Why do we do that? To save time, basically. Let's say full analysis takes maybe like 4 hours to run. Half would take around 2.5 hours, and the quarter would take 1 hour, 15 minutes maybe, right? So in order to cut time and get to our answer as fast as possible, right? So that's why we run it. And when do we run it? When we have symmetrical runner, right? So let's say if if we have a mold, and if we divide it into two halves, if both the halves are symmetrical, then yes, you can get to your answer by running half of the mold, right? So that's when we run it. And if all the quadrants of the mold you have symmetrical runner design, symmetrical parts, then what you can do is you can just run a quarter of the mold and get to your answer. If you are running into or troubleshooting any issues inside the mold, like shrinkage, warpage, or air traps, things like that, you can get the answer of your complete mold by just running a section of the mold, right? And there are two approaches to this symmetry. One is accurate modeling without approximation. So this is a default one, which I'm going to show you in the upcoming slide. And another one is branched modeling with runner volume approximation, right? So we're going to talk about both these approaches. So the first one, which is highly accurate, which is without any approximation, and that's the default setting we have when you select the symmetry. Another one is the branched modeling when the runner volume approximation. So what are the pros to this, right? Modeling is super easy, right, in this, and model size is small. You are not considering the entire mold, but you are just considering either quarter or the half. Computational time is significantly reduced. So this is the bottom line, right? We want to reduce our computational time, right, and get more in less time, right? And you can improve your speed by using symmetry function. You can run more design changes, iterations in same amount of time as compared to full model analysis. Let's say if I have 8 hours in a day, right? If my simulation, like a full model, takes 4 hours, I can only run like 2 simulations a day, right? But if I want to try maybe 15, 16 different designs, it might take me several days. Rather, I would just run quarter, and I could get 8 iterations done in a day. And also remaining, I can queue it. So within like a span of like a day, I can get so many iterations done by using this kind of functionality. So that's where it's helpful. There are some cons to it. Yes, extra manual effort is needed for geometry runner approach, which we're going to talk about, but it's going to be minimal. It's not going to be too much. It's going to still save you significant amount of time compared to running the simulation on the complete mold. Right. And symmetry settings should be correctly modeled considering the shear imbalance. We're going to focus on this because this is important. Why? Because runner, the shear imbalances within the runner and all the branches, it's important to consider that. So we're going to talk about that. And then branched modeling approach will approximate the runner volume. So we're going to focus on that as well. Like, how does it approximate, right? So this is the overall picture of what the symmetry looks like. And this is what I meant. So let's say if you have 16 cavity mold, right? And I can see here that this quadrant is exactly the same like what I have here, here, and here, right? So why not run the simulation on this and understand the root cause of the problem? Because that's what the whole idea of simulation is, right? You want to understand the root cause of the problem as fast as possible and move to the next one, right? So that's what we do in production. Like, hey, find the solution as fast as possible and quickly move to the another project and solve it, right? So that's what we're going to do. We're just going to run symmetry on this half. And in order to do that, all you have to do is select the model, click on this symmetry function, and then select if you want to have like a quarter or if you want to have like a half of the mold as a symmetry. And then once you select this, you just run the mesh, and this is how it's going to look like. So it's going to run simulation just on one half which you selected, right? But it's completely okay, right? It's using boundary conditions, so it's assuming when you select symmetry, it's assuming that there is, three other quadrants in this. So even though the simulation is run on this one, it's assuming the other three quadrants exist. Yes, you're not going to see the results on those, but the pressure prediction and everything, it's considering all four quadrants. Yeah. So this is basically showing the button, like how to go about setting this up. And another approach, which is approach number 2, which is branched runner approximation. So what does this mean? Basically, this is when you are, when you have a very complex geometry, when it's hard to control the mesh and the mesh size is getting crazy large. What you want to do is you can use this approach where what you are considering is, instead of considering one quadrant which has 8 cavities, you are just considering like a 1 cavity, right? And what you are estimating is basically how the runner flow would look like. So that's what you are designing here. So what I would do is I would just draw the runner for that 1 cavity, right? And then I would use this attribute wizard to basically mark that, hey, there is a connection, there is a flow on the other side as well, right? So there is a branch that gets split here. So I would mark this splits, and this is how it would look like. So material flows from here. Yes, even though I have just designed this, it knows once I define this symmetry axis, it knows that, hey, material is going to flow on this side as well. Yeah. And then same thing here at this particular junction, even though I have this particular geometry going this way, once I define the symmetry axis, it knows that, hey, material is going to flow this way as well, and we have exact mirror of this on the other side similarly. So you have to be really careful and understand where this material is splitting, and clearly define it exactly how it's supposed to flow, right? And double checking always helps, but this 1 cavity actually represents all the 32 cavity. That's what it tells you, right? So this is showing how the material is going to flow, and it's considering like, hey, even though you don't have the mesh for the other 32 cavities, once you define this symmetry axis, it knows that, hey, the material is going to mirror the behavior what you are doing it on this side. Yeah. And it works with the hot runners only at this time. So when you have hot runners, yes, it does work with that. And volume error depends on the sprue size. So there might be some relative approximation error, which is completely okay. You'll still get an answer, but just have to be careful you design it correctly on how the flow is supposed to be. So we ran simulation on both of these approaches. So we ran simulation on this one and the other one, and we looked at the results, and the results look exactly the same. We looked at the filling pressure, and you can see there is slight differences, not too much between the two. But yeah, it aligns perfectly. So basically what this tells us is like, hey, I can make my decision by running 1 cavity rather than all 32 cavity, which is going to save significant amount of time when I'm running into time crunch, right? So rather than waiting for hours or days, it can get my simulation done within few minutes when I use this approach. But there is a catch to this one, which we're going to talk about in the upcoming slide. But yeah, the conclusion is approach 1 is the preferred way. If it's feasible and not much effort is needed, then go for approach 1. If approach 1 is not practical, then go for approach 2. What it means is basically go for this approach. This is just selecting symmetry and defining like, hey, is it half of the mold or is it the quadrant we are considering? The only reason why we go into doing this is either we are running into time crunch, right? Or if the part is so complex that it's impossible to get 8 cavities meshed because it just increases the size, then there is a way of running it by this approach. Yeah. All right, and this is what I meant when I said there is a catch to it, is basically correct symmetry modeling based on shear symmetry. What it tells us is basically like when you have this kind of 32 cavities, rather than running just a single cavity, make sure you have 2 cavities. Why? Because of the shear balancing. We want to capture the accurate shear balancing, at least where the parts are, at least where the runner branch, which is touching the part, and the secondary one, which is connected to that, right? Once we have that accurately, it's going to give us highly accurate results. Doesn't mean that this is not going to give us accurate results. Yes, this is going to give us accurate results as well. But if you want to get more and more accurate, we want to consider shear symmetry. So better approach would be having at least 2 cavities like this design, and having to design these kind of both the runner system, the one that is touching the part, and the branch that is touching that branch or extending out of that one, right? And this is called shear symmetry. So why do we want to do that? We want to make sure that we capture the shear behavior accurately, except for the first, second, and third level of branches from the part. Yeah. Yes, this is still going to give you much faster results, significantly faster results than considering the entire 32 cavities, and you can get to your answers much more faster, right? And you can see that there are slight differences, not too much, since it's a easier part. But the bottom line is, yes, we want to consider the shear effect, and you can see like slight effect on the flow. One side is filling a little bit faster compared to this side, so there is some differences. But yeah, as the parts get complicated, we want to capture that the shear behavior, right, and understand what goes into it. Now, let's look into what is the line-defined runner and why to use it. Okay, so we're going to talk about what does this line-defined meshing means. It's nothing to do with symmetry. It's just a different way of meshing it when you have a multi-cavity tool, right? So we are complete. We are done with the chapter of symmetry. Now this is a line-defined runner, and how do we go about doing this? So basically, it is a representation of a runner system using a center line of the cylindrical runner, right? So that's what it is, and it's a true 3D representation of the model using hexa elements. Hexa elements are cubes or cuboids, which are considered to be highly accurate, and that's what this line-defined runner geometry gives us. What are the pros to it? Modeling is quick and easy. And as I said, hexa mesh elements are higher quality elements, and that's why it gives you the highest level of accuracy. More organized elements that helps with the consistent results, and you'll see it in the upcoming slide. We have some examples and pictures showing that. And variation due to mesh discrepancies are minimized. Why? Because it's consistently distributed. So the variation, that is less likely that there might be variation, especially when you are looking at these kind of multi-cavity tools. And uniform size elements and quality helps model shear imbalances easily and accurately, right? When you have uniform element size of each mesh distributed evenly, uniformly, and that really helps us calculate the pressure, the shear imbalances quick, with highest level of accuracy. What are the cons? Dimensions have to be measured for one leg of the runner system. What it means is basically once you get the geometry or the complete, all the cavities in the runner, all you'll have to do is you'll have to spend few minutes measuring what that runner branch measures at. And then non-cylindrical shapes cannot be created using line-defined geometry. So if you don't have like a cylindrical runner system, then you cannot use this line-defined runner. But yeah, we're going to look at the workflow now, and this is what line-defined runner system means, right? So let's say you have a solid geometry runner system. So this is the CAD or the step file we get from, let's say, SolidWorks or Creo that you're using. all we are doing is we are just extracting the center lines, right? So all you are doing is you're extracting the center lines from it, and then you are creating a line defined runner system on top of that. Yes, it looks the same, but it's not the same. What we are doing here is this is just getting the CAD directly inside Moldex3D. But what this line defined is you are exporting the center line and then creating a line defined runner system on top of it. So solid geometry runner, which is basically the actual geometry. So when you have the CAD model, which is this one, right? You just take the CAD model and run it. And this one is the line defined runner system. So now we are talking about directly using the one on the left, which is solid geometry runner system. So what are the pros and cons of that? Basically, it is the actual step file of the runner as created in the CAD software, whether it's SolidWorks or Creo. And meshing of the runner and part, what it does, it gives the same size for the elements, and that could lead to some quality issue. And that's why we prefer going line defined geometry. Yes, it is okay to use it, but when you run into this kind of multi-cavity situation and considering the highest level of accuracy when it comes to the shear, we want to go with the line defined geometry. So yeah, modeling is quick and easy because all you are doing is basically taking a step file from the CAD, importing it inside the Moldex3D Studio and running the simulation, right? Less human involvement in the modeling process. You're not spending time in measuring and creating like a line defined. You are just directly running simulation on top of it. And non-cylindrical shapes can be easily modeled. Yes, you can easily mesh how you bring in the model inside the software. So there is no additional work required. What are the cons now? Geometry cleanup may be required. So especially with these kind of high cavitation tools, this kind of modeling process might require geometry cleanup, right? Part and runner mesh size have to be same. So you have to make sure that the part and runner mesh size is exactly the same. Otherwise, it's going to create some issues. Resulting mesh might not be symmetric, causing artificial numerical cavity variation. So there might be variation from cavity to cavity, depending on how complex it is. And a lot of tetra elements in the runner, which could lead to some inconsistency in the results. As we said, like hexa elements is something that we prefer. So in this case, it's producing a lot of tetra elements, which is accurate, but not as accurate as the hexa element, right? So we want to go with the top-notch elements inside our mesh when it comes to the high cavitation. Mesh generation time is high. Yes, even though you are spending less time in preparing the CAD model, mesh generation time is high, right? Which is the opposite with the line-defined geometry, where you are spending a few more minutes in creating and measuring the runner and creating it inside the Moldex3D. But your results are highly accurate and your mesh generation time is lowered by that, right? And editing the mesh is tedious and time consuming as well. Like in this case, you are spending time in fixing the mesh and that could take up some time. But on the other side, on the line defined, you're not spending too much time on the meshing because it's fast. And these are the two differences basically. On the left hand side, what we did is we took the part as is from the step file, run the mesh on it, and this is how it looks like. You can see a lot of tetra elements, but this is the line defined where you are creating the center line, exporting the center line, measuring the diameters, and just creating a line defined runner system. Both are exactly the same. All you have to do is just measure the diameters and create it. Yes, you're gonna spend little time here on the runner creation, but you're going to save significant amount of time in the meshing, cleaning up the mesh, and also the accuracy is going to be way too high, right? This simulation was simple, so we don't see a lot of differences from left to right when it comes to the runner, but when we zoom in, right, you can really see the differences. You can see that the outside temperature is much higher compared to this one. And hexa elements, as we know, produces highest level of accuracy. So this one would be much more accurate. And yeah, so in this case, shear is really important, especially for shear sensitive materials and the complexity of the part. So we want to consider the line defined runner for that. So what are the key requirements, right? Best practice for meshing solid geometry runner. The resulting mesh of the entire model should reflect the symmetry of the geometry, right? So that's what we want. When we are trying symmetry, we want to make sure that the whatever quadrant or half of the mold we are considering is exactly symmetrical to the opposite side. Even the cooling lines, right? We want to make sure that the cooling lines, or if you are using elastomer rubber material, we want to make sure that the heaters are exactly aligned. So that is also important. Not just the runner and the part needs to be symmetric and oriented symmetrically, but also the water lines needs to be symmetric. So please make sure that that is symmetric, and you are considering the half or the quarter based on that. Use symmetry to have more iterations in same amount of calculation time. We already talked about that. Like, what's the benefit? Saving so much time, right? Take advantage of repeating elements. So if there is any parts that are repeating, just create copies, especially the functions where you have to create like a 2 cavity for shear. You can use that, and also some update on 2022 versus 2023. So model the part and the runner system with the same size element. What we found is in 2022 version, it was a mandatory requirement to get good quality mesh. But in 2023, the improvements have been done by R&D in meshing kernel, and that has relieved this requirement. But it's still highly, it's highly recommended to model the part and the runner system with the same size of the elements. Right? So part geometry and high cavity layout. So this is the this is the example we're gonna use. This is the 32 cavity tool, and these are the dimensions of the part. It's about 2.5 inches height, 5 millimeter thick on the wall section, and this is how the mold looks like. So what are the improvements have been done in 2023? So in 2023 version of Moldex3D, meshing has improved further. So matching mesh between runner and part is almost possible every single time. So that was an issue in 2022, but now it's completely fixed. So now there is a matching mesh between the runner and the part, and you can see it right here. So it's very consistent. The only exception would be when you have a gate in a very constrained area, right? So where you have like an edge which is at an angle, or a weird feature where you have a gate which is at an angle, that's when you have to double check and make sure the mesh is. But I would say 99% of the time, it's gonna get you consistent mesh between the runner and the part almost every single time. And then this is the recommended workflow, what we recommend. So this is basically taking all the learnings what we had today, symmetry, line define, everything, and putting it into place basically. So let's say if I get a mold tomorrow that my team wants me to work on, right? So this is what I would do. This is what the recommended workflow is. First thing I need to do is clean the geometry from CAD Doctor. As you can see, CAD Doctor is going to take up, do all the heavy lifting of cleaning up the mesh and the geometry, basically. So what we want to do is, when you have the geometry ready, the step file, bring it inside CAD Doctor, clean it up, make sure it's ready to go, no issues or no errors. And CAD Doctor is so powerful; it's going to help you, fix any minor issues, whether it's been on the CAD side. It's going to automatically help you fix it. Extract center lines for one repeat unit, at least one quadrant. What we want to do is we want to extract the center lines from the CAD and assign the property of cold runner or hot runner to it. So what we want to do is we want to assign the property for this center line as cold runner or hot runner, and create a surface mesh on single cavity. What we want to do is we want to create a surface mesh first, at least on the single cavity. And all these steps we're going to look at in a picture for a more visual format in the upcoming slides, but I just wanted to run down through what the steps are, so anybody who gets the copy of this presentation, they have it. So whenever they have a multi-cavity tool, they know what to do step by step. Use mirror function to create the half or the quarter cavity. So basically, yeah, use the mirror function or copy function to quickly create, if you need multiple parts or copies, you can quickly create it. Use the symmetry function to either on one quadrant or half the mold. But we want to make sure that, whatever half you are using or quadrant you are using, all the other quadrants or other half is exactly similar, right? Even the water lines, right? Use symmetry function to see the exact layout before it is stored away in memory. So what it will do is it will show you before the meshing and before running the simulation to make sure that everything looks okay. Final meshed model with symmetry boundary condition applied. So we want to make sure that every final mesh model has a symmetry boundary condition applied, and you can check it. So this is the typical workflow of all the steps we discussed. So what the first thing we do is clean the geometry from the CAD doctor. That's what we did. And now we're going to extract the center lines, right? This is what we have, and this is the step, right, for it. And then we're going to assign the property of cold runner or hot runner to it. So it knows that, hey, this is going to be my runner system. And then we're going to create a surface mesh on the single cavity. Then what we're going to do is we're going to copy this cavity and make copies of it to attach it to these gates. And that's what we did. Use mirror or copy function to create all the other cavities in that quadrant. And then we're going to use the other symmetry function. And this is what I mean by, imagining like, hey, this is how my final layout of the tool is going to look like. I want to make sure that it's accurate, it's symmetrical, and it represents what you have in the production or the prototyping phase, right? So this is what it's going to show you as a visual. Like this is how it's going to look like. But yeah, we are running simulation just on one quadrant. And then use the symmetry function to see the extract layout before it is stored in the memory. And approach 1 is shown here. Approach 2 might be feasible too. So we are just looking at the approach 1 out of the 2 we did the meshing approaches. And this is how the mesh looks like. Right? And you can see that the mesh inside the runner system is all hexa. So we know that it's highly accurate. This is the mesh model, and result depict this model in half the simulation time. So results are still depicted on this, but we are actually running simulation on this, and it's just creating a copy of this exact one. And we are comparing the pressure of all the three, and you can see you don't see much difference whether you are using like a full model, symmetry, or the symmetry with the line defined. But the only thing we are going to save is so much time. And this is basically showing you the differences, modeling time and computation time, line runner with the 30. So basically, when you're considering the entire mold, it takes around like 4 hours of total time, right? 1 hour of modeling time and 3 hours of computation time. But you can get the same answer. Let's say air entrapment is an issue, right, on all your cavities. You can get the same answer within like 30 minutes. You don't have to wait for 4 hours by following this approach. Yeah. And this is the machine spec. We use the same machine for all of them. So now what we're going to do is we're going to talk about cost-effective progressive analysis. Like what are the different ways you can improve your analysis when it comes to the multi-cavitation tool. Coarse grain versus fine grain analysis. We're going to talk about single cavity optimization, considering the actual cavity, and then the full runner optimization with simple cavity, and then connecting both of them, cavity, optimized runner, and running the further analysis. Right. So single cavity optimization. So you want to have the most precise result for the cavity. You should have the most of your elements in this cavity. So what it means is we want to make sure that we have finer mesh inside the single cavity. Make sure that the gate is okay. Make sure the part has representing the CAD and has the finer resolution. And then what we want to do is we want to optimize the runner layout. So what it means is when you have a 32 cavity mold, right? And let's say you have a complex part. This is really important, right? So when you have a 32 cavity mold, and let's say you have a complex part, right? And what you need to do is you need to focus on what your goal is. So in this case, my goal is to optimize the runner system, right? So at this point, I don't care about my part, right? I just want to optimize my runner system so that the flow is balanced in all the 32 cavities. So what this tells you is that you don't need to have that complex geometry as your part for all the 32 cavities. You can just create like normal cubes or squares until you optimize your runner system. That is going to save so much time because you can just create like a dummy part. It doesn't have to be any representation of your actual part, because right now I'm just focused on optimizing the runner system. Yes, once I optimize my runner system, then I can consider my actual part and make sure that everything is balanced. So that's what this slide, or the most important takeaway from this slide is. You can use the dummy part instead of actual part, and it's easier to change the dimensions with the line defined runners, and dummy cavity can be small so that the simulation time will be short. So why are we doing this? To save on the simulation time when you're optimizing the runner system. Right. So now what you can do is, once you have the final optimized runner system by considering these kind of dummy parts, then you can bring in your actual part and run the complete analysis to make sure that everything looks okay. And yeah, so this is just some time saving steps that hey, if your goal is to just optimize runner system, you don't have to worry about how the part looks like. Just make sure that you have some dummy parts. Make sure you focus on optimizing your runner system, try different dimensions, some diameter changes, whatever it needs to be. And once you have that optimized, then you can run the final iteration. So that's going to save you so much time. One thing I wanted to let you folks know is that, hey, when you have when would I consider running a symmetry versus running the complete mold, right? So let's say my issue, right? My issue is related to like air traps or shrinkage warpage. In that case, what I would do is I would just run like a single like a symmetry like this kind of line defined. Why? Because all of my cavities are showing the air trap issues, or all of my parts are shrinking and warping the same way. So in that case, like, hey, even if I run these two cavities, it's going to represent what's going on in the other cavities, right? But if I'm running a situation where I'm running like imbalances of the runner system, in that case, I need to evaluate the entire runner system, right? And I want to find out if it's coming from the runner. In that case, what I can do is I can just use the dummy elements for my parts and try to find out like, hey, if my runner system is balanced or not. So it all depends on what your goal is for the project. When you are trying to understand if you are focused on the runner system and trying to balance it, yes, it's important to run the entire runner system. But if the goal is just to understand the root cause of air traps, where is it coming from, or shrinkage, and if all the cavities are experiencing the same shrinkage, similar shrinkage, and similar air trap, then yeah, you can just get one or two parts and get the answer of what where that could be coming from, right? So that's the whole idea. First, we need to focus on what our goal is, and then based on that, you can figure out your next plan of action on what we need to do. So that's all I have on the meshing side. Hopefully that was a good learning experience. And other things I wanted to share, this is just quick miscellaneous examples. So basically, machine consideration. Yes, everybody knows that we have. You can consider the machine inside the simulation using the machine mode, and this is really important when you are in the earlier machine selection phase. So we have a database of around like 1,000 plus molding machines, and you can use your exact molding machine to understand if my pressure or clamp tonnage requirement would be enough or not. So those are the things you can consider it. We are also working with all the major machine manufacturers, so that once you optimize your process, you can machine can read it, and similarly whatever settings you have inside the machine, simulation can read it. So we are creating this back and forth loop to connect the machine to the simulation world. Another thing is Gate Advisor. So this is the enhanced Gate Advisor. I would highly recommend you folks to check it out. It's not just the Gate Location Advisor, but if you type in Gate enhanced gate location advisor Moldex3D. It will take you to this link. And what it does is basically when you are in the initial part design or part development phase, we want to find out, it will help you identify quickly where the gate needs to be, what are the ideal location for the gates. You can also mark like, hey, I cannot have gates in these, critical areas because they are, aesthetic, for requirements. What it will do is it will try to find out, the best gating location without placing the gate on that area. So there are various different features in the enhanced gate location advisor you can try. It's really helpful. And it's super quick within few seconds because it doesn't run simulation, but it just considers the flow to length ratio, and it will quickly find out the approximated gating location for you. And yeah, there are several different case studies on our website, so do check it out. 6,000 plus case studies from various different. Also on YouTube, like if you have, let's say, any molding issue like sink marks, all you have to do is sink marks Moldex3D on YouTube, and it will take you to several different examples, or air trap Moldex3D, or how to optimize gate inside Moldex3D. It will take you. So wanted to put it out there that we have so many videos that we have created in the last few COVID years. So there's a lot of resources. You can check it out and see, if you find relevant information through that. Another thing is we are also focusing on the automation side this year. So basically what it means is we want to automate, the machine, the simulation setup and the report generation for our users. So in this particular example, what we are doing here in this video is we're going to do all these functionalities automatically. So it's going to create a project file. It's going to automatically import the part geometry. It's going to place the number of, location of the parts in the script. So basically we have used the script to write these codes, and it's running everything automatically. It's going to create gate using the gate location advisor. It's going to create generic cooling layouts. It's going to automatically generate the mesh for you. It's going to select the material, what you need to define. It's going to create the process file. It's going to run the simulation and also automatically populate the results that you care about, right? So everything can be automated inside Moldex3D. And if you would like to learn more about it, let us know, let our support know, and we can talk about it. But basically, we want to eliminate the labor that goes into setting up simulation and creating the report. Also, there is ways where it can create like alerts for you, right? Like you can mark it like, hey, once the mesh is complete, before hitting the start button, just alert me so I can double check everything, make sure everything is right. So that's what it's going to do. But yeah, focusing more and more towards the automation side. We have ISLM. I hope you have already looked into it. But basically, what it does is it's a database of actual simulation data and production data all in one place. So you can compare past projects, take all the learnings, and apply it on the future projects automatically. Then Material Hub Cloud, which is the database of around 9,000 materials. We have Viewer. So if you want to send results to your clients, you can ask them to download the Viewer, and you can send them the Viewer file. And Viewer file is not just images or animation, but it's actually very interactive. So you can zoom in, zoom out. Users can actually slice it and see what's exactly going on. And you can mark it to your clients like, hey, we cannot place a gate here because we have an issue or aesthetic issue, or there is a hot, or whatever you want to mark it. You can mark it so they can zoom in, rotate it, read it, and get going. But that's something that we wanted to share. Also, we are not only the simulation and focusing on the automation side, but through our partner companies, we are also opening the supply chain needs, or helping with the supply chain. So if you need help with the tool building, like actual physical tool building, we can help you out with. If you need help with prototyping, we can help you. If you need, if you're running out of capacity issue, we can also make parts for you. Following the T0 scientific method, so everything is performed scientifically during the molding process. Also, automation. Like if you want to automate any of your cells, we can help you automate that as well. So that is something that we are also providing. So if you need help with, let us know and we can help you out with that. So it's a one-stop shop basically for tool building, prototyping, simulations, everything. And we make sure that the communication is at each and every step, so you get the most optimized solution. But yeah, we are offering our online half-day online training. It continues, so there is a schedule online if you want to check it out. Webinar series like this one, we have it going on. 3-day in-person training in our Farmington Hills, Michigan facility. If anybody wants to, join in for that, feel free to reach out to us. As I said, a lot of YouTube resources, so please check it out on our website and on YouTube. Social media, this is important and this really helps us out. So if you can follow us on LinkedIn, that really encourages us to put out more and more technical content for our users and keep you updated with what's going on in the simulation world, and also how folks are using it in order to solve their real life problems. With that, we'll move towards the university partnerships that we offer, and also the symposium. We're going to host it next year. Last time we did it, we had around like 270 participants. So this is a good networking event, and I would recommend each and every one of you to at least look into it and see if you can attend. You'll get a lot of value out of that as well. All right, with that, I will conclude our presentation and take on any questions. And if it's highly technical, I might have to forward it to our support team. But thank you for your time, and have a nice rest of the afternoon.